The BMW M3 is always touted as driving excellence, so many people have a hard time believing that its aerodynamics can be improved. In this video, we'll show you not only how they can be improved, but how they can be improved very easily using just these two little pieces, a front splitter and a rear spoiler. As we'll see, their effects are very different to what you might expect, and this large rear spoiler really puts the stock spoiler to shame. In fact, this idea doesn't actually come from us, but from one of your amigos who goes by the name Mr. Ziski. So this regular E92 looks good, but its aerodynamics are actually pretty bad. We simulated at 130 kph, which is faster than anywhere around where I live, if you follow the speed limit, which I always do, because I'm a responsible adult. So the front is largely good. There is one region where the flow really decelerates. You can see how blue it becomes. That means its velocity is almost zero. So the flow slams into the front, dumps its kinetic energy, and creates a lot of high pressure. That increases the drag. That's not great. But the front is actually a lot better than it might be. Look at how the top half really guides the flow over it, and we don't get too much more deceleration here. That's pretty good. Much better than most cars. So really, only the bottom half of the front is bad. As for the underneath, it's also really good. So there is a sharp lip, but underneath, the flow still stays attached. That is way better than most cars because most cars get flow separation underneath. By keeping the flow attached and nice and streamlined here, the drag drops. This region actually highlights something that I think is wrong with the automotive aerodynamics industry right now. After having worked in it, it's very copycat. As soon as one car gets a lower drag coefficient, everyone tries to copy it, and usually without fully understanding why various features behave the way they do. We see the exact same thing here where the front lip is better than most cars right now, and yet somehow the industry got turned away from it. It doesn't help that this car's drag coefficient came in at 0.33, which is pretty bad. But that doesn't mean that the entire car's aero is bad. And actually, as we'll see later, is mostly because of the diffuser. This front lip is actually really good, and the few cars that have a similar one today reap the drag benefits from it. The reason why this lip is so good is because BMW just angled it up a little. It helps with ground clearance, but also by angling it up, it reduces the angle the flow has to turn around. If the lip were horizontal underneath, the angle would be around 135 degrees, but here it's more around 100 degrees. That might seem like a lot still, but because the lip is so slanted, it also squeezes the flow, so the flow underneath is constantly being pushed up and forced to stick to the underside. That's really good. Well done BMW for this. The front of the hood is okay, we do get some drag here, but I think that's mostly because you get high speed flow jumping over this gap. So some of it is getting caught up in the lip, and that creates a little drag. It's not much, but it's something. On the hood, we see a pretty cool embossed section. On the face of it, it might seem really bad because you literally have this thing poking up into the high speed flow. So now the flow has to go around that too. But in terms of drag, it seems fine. The flow decelerates a little as it hits it, and that comes with higher pressure. But just after it, we get even lower pressure as the flow is forced to turn around the edge. So I think the amount of local drag from this is minimal because the pressures kind of cancel out, and the high pressure wasn't too much to begin with. Also, the amount of surface area this acts over is quite small too. So overall, it's fine. Having said that, it does make the downstream section worse though. So as we've seen in other videos, this junction between the hood and the windshield is very important. The more disjointed it is, the more the flow will crash into it, decelerate, and waste its energy on it. That also comes with high pressure, which pushes the car back and creates more drag. We definitely do get that here too, and very few cars don't have this region. And that's because you have to put the people somewhere, and the results are this cabin forming. So it's not really about removing this junction, but rather making it as sleek as possible. The embossed hood does the opposite here. It makes the hood section right before the junction flatter. That increases the angle between the hood and the windshield and makes it more disjointed. As a result, the flow crashes into the windshield more, and that increases the pressure here. So the flow is pushing the car back more, which is drag. So while the embossed region doesn't locally affect the drag, it does affect the drag downstream. Just as a side note, if you'd like us to simulate your very own car and modifications, let us know here. Now we come to the roof. It's okay, not great, not bad, pretty average. The flow accelerates a lot over it, as it does with the average car, and that comes with low pressure over the entire roof too. So we get a lot of lift. For the average car, lift is okay, but the more performance oriented the car is, the less you want that lift because it reduces grip. One thing BMW did to the E92 version, so this coupe version, which actually improved the roof flow, was to make the car a little longer than the four-door version, the E90. The reason that's good is because it allows you to blend the roof into the body more. The more length you have to work with, the more you can accommodate the cabin. So that helps the roof flow approach an average flow. One thing that could have been done better is the rear of the roof and the rear window. BMW made the rear window and trunk very distinct from each other. That increases the slope of the rear window. And as we've seen in several other car videos, that increases the back pressure pushing up. That then increases the boundary layer thickness growth. We cover this phenomenon in more detail in last week's video on why the old Porsche 924 was freakishly aerodynamic. The thicker boundary layer here has the same effect, where it simply increases the wake size and hence the drag. Now, the reason why BMW made the rear window and trunk like this, other than styling, is to reduce the rear face's size. From that point of view, they did a great job. The rear face is small, as it should be for a sedan. That's important because looking at the pressure, we get low pressure here, and that alone will dramatically increase the M3's drag. So reducing the face size is definitely helping reduce the drag here. Another benefit to this disjointed rear window and trunk region, we do get high pressure at the back. That then pushes the rear into the ground more and gives the car more downforce. That downforce is partly because of the small rear spoiler. So we can see how this small rear spoiler does more than just kick the flow up. In fact, looking at the velocity plot here, it doesn't even really do that. It's too small. But by sticking it up just like that, it does act like an obstacle to the oncoming air. That then forces the air to change direction, which then creates higher pressure. So while this tiny spoiler doesn't seem to do too much to the wake, I mean, if you were to follow the line of the trunk without the spoiler, that's the path the flow would take without the spoiler into the wake. Then compare that to the direction of the flow with the spoiler, there's not a whole lot of difference. So the spoiler produces only a little downforce from that region, but by acting like an obstacle for the flow upstream to crash into and redirect, it creates more downforce through the resulting high pressure over the trunk. It's a pretty clever addition that many cars have since adopted. But we'll see later how an enlarged spoiler affects the flow, and just a quick heads up, it's really surprising. This spoiler region has so many indirect effects away from the actual spoiler. Anyway, moving on to the diffuser. This is the bane of many BMWs. We hammered the M2 about it, which was warranted, and actually it was pretty funny. So after we pointed out the M2 flaws, we had something happen to us that has never happened to us before. Some people, I guess angry M2 owners, tried to get YouTube to take the video down. We received an email about it. This video is still up, by the way, and here for anyone who wants to see it, lol. Or maybe we should also pin it to our homepage. That's a good idea, yeah. Anyway, so this M3 has the exact same problem as the M2. Its exhaust hangs down. It might not seem like a big deal, I mean, it's pretty rounded, but the diffuser is perhaps the most important aerodynamic region of the car. It has the ability to reduce the drag by 20 or even 30%. And that's also while increasing the downforce. That is incredibly rare. Usually you get one, but not the other. So anytime you want to put something disjointed on the diffuser, like sticking an exhaust out, that's going to mess the exhaust performance up. And we see that exact same thing here. We get a larger wake, which increases the drag, and the flow is now down at an angle, which tells us that we're getting lift too. You'd be hard pressed to make the diffuser worse than his. I mean, to illustrate just how bad this is, as I mentioned, a diffuser normally reduces the drag and increases the downforce. Here it's increasing the drag and reducing the downforce, the exact opposite thing to what it's supposed to be doing. It just sucks. And that's really surprising to me because we see the exact same problem across a bunch of different BMWs over more than a decade. Whatever the reason was, it must have been important just given how bad this aero is now. And also considering that now, if you're over a certain limit of CO2 emitted per kilometer, the company has fined a certain amount per car sold, and that obviously makes the cars more expensive. So perhaps it's a packing issue, where the exhaust had to be put there, otherwise a major redesign would be needed. I don't know. Anyway, that's the center plane. Let's now move over 50 centimeters to the left. The flow here is pretty good. The front, if anything, is better than the center plane because we get pretty much no major deceleration. There's a little bit, but the flow is still over 70 kph. The front wheel spoiler is doing pretty good. It's a little hard to tell in this plane, but in the streamline orbit, we can see that it pushes the flow around the front wheel nicely. This is actually very good considering that this car was designed when front wheel spoilers were just coming into the market. So the fact that BMW made this good, this early on, is impressive. But one thing I'm even more impressed with is the flow behind the rear wheel. Now, we're to the side of the exhaust and actually on the inside of the wheel, there is a little bit of a wake from the wheel, but it doesn't flow into the diffuser that much. We can see here how the flow is nicely behaved here. The rear wheel wake isn't flowing inboard into the diffuser so much because actually that exhaust box kind of stops it. So while it ruins most of the diffuser in this plane, the diffuser is actually better because of it. Over the rear window, we have some pretty bad flow. You can see how this streak of slow green flow forms. That's actually a C-pillar vortex, which is very bad for drag. Most modern cars have eliminated that and the drag they create. We can actually see it much more clearly in the streamline plot, where the flow from as low down as the mirror height jumps up and over the rear window. As it does that, it rolls up into a vortex. The reason why it forms is because the C-pillar, so this structural pillar at the back, is too angled down. That is also part of the problem, as we mentioned earlier, about the rear window being angled so much, and that creates a large boundary layer. If you take the top of the rear window and extend it to the end of the trunk, that line is much shallower. That shallower angle will reduce this tendency for the C-pillar vortex to form, and that's how most modern cars have removed that vortex. At this time, this approach wasn't really done, so it's easy to see why it's happening here. Moving to this plane, which is 20 centimeters off the ground, we see a glimpse of what was to come for many cars. So you can see just how the big wakes from the front wheels are forming. That has a lot to do with the front wheel spoilers. So we said how they were doing a good job redirecting the flow around the front of the wheels, but by doing so, you can reduce how much fast-moving flow, high energy flow, is crashing into the front of the wheels. That then reduces the high pressure on the wheels as you're not wasting as much kinetic energy on them. A side effect is that the front wheel wakes become huge. With that comes a lot of drag, as we can see here. It might seem counterintuitive that these front wheel spoilers are then reducing the drag of the car. I mean, if the front wheel drag is so high now, that must mean more drag. But because the front wheels are at the front, anything that happens to them then flows downstream and affects everything else. While the front wheel spoilers do increase the drag in this region, they reduce it elsewhere. For example, the underbody is now seeing cleaner flow. That then drops the drag along the car and even the diffuser. So you see it all the time where modern cars load their front wheels with drag only to reduce the drag elsewhere, and that reduces the overall drag of the car. Now, another major potential benefit of front wheel spoilers is that the wake from the front wheels then can flow into the rear wheels and reduce the drag there. That's because the flow is slower now, and you're going to get wakes from them anyway, so why waste good flow on them? As a result, you get less drag from the rear wheels. I said this was a potential benefit, but not always the case. It really depends on the geometry of the front wheel spoilers and then how they redirect the flow. Here they're done very well. We get the modern high drag at the front wheels and low drag on the rear wheels, so it's cool to see this pattern so early on. These simulations were done with OpenFOAM. If you'd like to learn OpenFOAM, then check out our courses here. We currently have an end of summer special on that I think you might like. Moving to the rear, we can see all these different patterns we talked about earlier in one picture now. You have the major wake in the middle That's from the exhaust ruining the diffuser flow. You then have the lanes of decent flow either side of that, which is clean flow going over the diffuser. You then have the rear wheel wakes outside of that, which aren't flowing inwards because the exhaust is in the way, and because the diffuser flow is ruined there, the pressure isn't low enough to pull that flow in. It's a pretty complex picture, but we saw each of these components of the flow in other planes before. In the drag orbit, we can see the damage of this region. The wake does feature quite a lot of red regions of drag. This is something that some modern cars have really tackled well though. Now, while at 20 centimeters off the ground, the front wheels have terrible wakes, at 40 centimeters off the ground, the flow here is almost perfect. There is almost no wake, and that can also be seen in the drag orbit, where there is no drag here either. This is also a telltale sign of wheel spoiler that has come to be known. There's a large wake down low, and then a much smaller wake in the middle section. There is one final region for this car, the upper section, which we can see there is quite a bit of drag coming from, but we'll get to that in the next plane. In this plane, let's focus on the rear half of the car. So the rear wheels are really good. One thing I really like is how there's no real turbulence behind the rear wheel, just a little. That helps the flow stay attached over the side and only separate once it hits the fairly sharp rear edge. You can see how hard the flow is trying to stay attached and even correcting itself once it gets hit by a pocket of bad flow. That's pretty cool. Having attached flow all the way to the wake, in the end reduces the car's wake and hence the drag. Now moving to 60 centimeters of the ground and back to the front wheels, we see a decent wake from it. That tells us that there's just too much flow in the wheelhouse and nowhere else for it to escape from. So it pops out the top, and we get a lot of drag because of it. In fact, this kind of drag production image is close to the quintessential one for a modern car. One way of reducing that wake is to give the car bigger wheels to occupy more of the wheelhouse volume. That would restrict how much the flow can go over the top. Another way is vents at the rear of the wheelhouses to help extract some of that air before it is blown out the sides. Another way is to put vents in the top of the wheelhouses to allow some of that flow to exit there too. Anyway, the rear wheelhouse is still doing very well here. It's kind of on the border now between good and bad because you can see how the flow is a little disorganized here. That is partly because of that sharp edge of the wheelhouse jutting out into the flow. Smoothing that more would help the flow travel along the side more easily. But still, it does stay attached, and once it reaches the rear, it separates well. The rear wake is good, it's very small. We have a few more planes, and they give us more of an insight into the flow around the rear spoiler, so let's save them when we're looking at the larger rear spoiler. Speaking of such, we also simulated this exact car with a front splitter and a much larger rear spoiler. The results are unexpected. So focusing on the splitter in the center plane, in terms of drag, it's pretty safe to say that this front splitter is increasing it. You can see that not only is more of the front decelerating the flow, but the speed drops even more. It's bluer. So more of the flow's kinetic energy here is being dumped into the front. That's always bad for drag. So why does this happen? So why it does this is because without the front splitter, the flow can go underneath the front of the car fairly unhindered. With the splitter, there's now this lip in the way, and the flow that has already gone past is pretty much stuck between the air behind it and then the front. So the flow above gets boxed in and has to decelerate. What's more, this splitter isn't long enough. You can see that the flow that goes around goes from horizontal to vertical and then back somewhere between the two. It has to redirect like crazy. That creates a bit more flow separation underneath, which comes with more drag. Extending the splitter forward more means you get less curved flow, and so the angle between the flow coming in and the splitter's underside is much less. As such, the flow will stay attached more and you'll get less drag in this region. That's in terms of drag. For downforce, the splitter is good, and this pressure plane clearly shows why. So the main way a splitter produces downforce is by making the flow above it decelerate and dump its kinetic energy into the front. That makes the static pressure skyrocket, as we can see here. That high red pressure area isn't just acting on the front of the car, but it's also above the top of the splitter plate. That's pushing the splitter plate into the ground and creating downforce, in addition to that, we get low pressure underneath as the flow is forced to race through there, so the pressure drops. So high pressure on top, low pressure underneath, that's downforce all round. That's how splitters work in a nutshell. But this pressure plot also clearly shows why they're bad for drag. That high pressure here is pushing the car back more, drag. So this device isn't affecting the car in any way that's not unexpected just yet. We'll see later, maybe that's not the case. I also did say that the results of these two devices were unexpected, and that's because the rear spoiler is incredible. So the drag coefficient of the stock car came in at 0.33. With the front splitter and rear spoiler, it dropped to 0.30, a 10% drop. That's insane, especially considering just how small these two devices are, and that splitters aren't really for drag reduction. Let's look at the rear spoiler to see what it's doing now. Behind it, the flow doesn't seem to be too different to the stock car. It's kicked up a little more, which is good for downforce. You'll get a little more from it, but because the wake is kicked up a little more, it becomes taller, which should come with more drag. I say should because we know that this spoiler splitter combination, that drops the drag coefficient by 10%. We know that it's not really coming from the splitter just yet, so the spoiler must be doing something here. Here, if the wake is taller, and logically the drag will increase in this region, where is the drag reduction coming from then? Well, the diffuser seems to be the answer. Looking at the stock version, the flow separates about halfway along the exhaust and flows down. So the wake becomes much larger. With this large spoiler, the flow underneath stays mostly attached over the exhaust. But even when it separates, the flow doesn't blow out downwards and cause a large wake. Instead, it sort of sticks to a pretty horizontal path and even floats up sometimes. That makes the bottom of the wake smaller, and hence the drag drops in this region. So while the large splitter is making the top wake a little larger, the bottom is really being improved. That's a little weird because the spoiler, which is located at the top of the trunk, is affecting the flow literally underneath the car. How is that possible? Well, by kicking the flow up at the top, you're encouraging the wake to move up in that direction more. That creates a void lower down, which then encourages the flow underneath the car to flow out. It's easier for the flow to travel horizontal now. So with the stock version, there's more flow in the way behind the lower part of the car, so the flow underneath the car is sort of hemmed in more. With this larger spoiler, that's not so much the case. So this larger rear spoiler is actually helping the diffuser perform better. By simply producing conditions that help the flow evacuate that region easier, the diffuser can lower drag and increase downforce. Over the top of the trunk, the large spoiler increases the high pressure there as expected. That also increases the downforce on the car too. Let's now jump over 50 centimeters to the left to see how the splitter and spoiler work there. Are they performing well now? Well, in one word, yes, they're doing really well here actually. So for example, the splitter is still having the exact same effect where the flow has to race underneath and drop the pressure. The flow on top decelerates and increases the pressure. So we get good downforce and all that. But that's not the region I'm too interested in here. The region I'm really interested in is the diffuser. So it's working really well now. This is really impressive. I mean, you have the wake of the rear wheel threatening to come in and ruin the diffuser flow. We have that somewhat happening here with the stock car. But here the diffuser is seeing almost perfect flow. There's still a little bit of a wake hitting it, but it's really good. So this rear spoiler is working incredibly well here. But you might be wondering if the splitter is also helping here. I mean, the flow over the diffuser will come from upstream. So maybe the splitter is also helping produce a nice flow here. I think there is definitely some benefit from it. We can see how the underbody flow is a little better now, and that will help with the diffuser. And actually, coming to this plane, 20 centimeters off the ground, with the splitter, the front wheel wakes are way worse now, but that actually makes the rear wheel wake better. You can see that it's smaller now. That is partly because of the slower flow hitting it to begin with. So this smaller wake, which flows directly over the diffuser, means that in this region, the diffuser has better flow to work with. So while in this center plane, the rear spoiler seems to help the diffuser work better, here, I think it's a combination of both the splitter and the rear spoiler. What about higher up? This plane is 40 centimeters off the ground, which is pretty far away from the underbody and also pretty far away from the spoiler. Do we still get an effect here? Well, this plane is really a tale of two halves. The first is the upstream half, which is worse with the splitter and spoiler because the front wheel wakes are much bigger now. That then flows downstream and makes the flow want to detach more around the rear. That's all drag. The reason why the front wheel wake is worse is because the splitter is making the wheelhouse flow worse. The flow underneath the car is faster and that gets into the wheelhouse and just makes more of a mess. It then has to exit somewhere and it blows out more on the stock car. But that's the front. The rear is a completely different story. So with the splitter and spoiler, the wake is so much smaller. That means less drag. And that's because the diffuser is working so much better now. And that's kind of the same story at 60 centimeters off the ground. The wake is a little smaller still, however, it isn't improved to the same extent as at 40 centimeters off the ground. So this shows that the improvement to the diffuser flow is starting to wear off here. But still, these planes show just how important the flow over the diffuser is and how a good diffuser can dramatically change the wake and the drag. Let's now jump up behind the spoiler to see how the flow has been affected by this larger one. This is 0.9 meters off the ground. Looking at the rear, with the large spoiler, the wake is a little worse now. It's wider and is more persistent downstream than the stock car. That makes sense because the larger rear spoiler is creating a larger wake in this region. So now we're cutting right through the spoiler and we're 1 meter off the ground. The larger wake behind the spoiler is obvious, but something a little surprising to me is that if you look ahead of the spoiler with a stock car, which still has a spoiler, but it's tiny, the flow blows out around it and still decelerates a lot. For the larger spoiler, we don't get that happening. That's because with this larger spoiler, it extends almost to the very edges of the car. So once we reach those points, we now have a much faster flow from upstream, hemming any flow in that might want to spill out. For the smaller spoiler in this plane, it doesn't extend to the edges, so the friction flow doesn't hem it in, so it can blow out more. So we know that with the splitter and the larger spoiler, the drag drops very nicely, but the lift produced is even more impressive. So the stock car at 130 kph produced 40.9 kilos of lift, not great. But with just these two small devices, that drops to minus 4.5 kilos. So it actually produces 4.5 kilos of downforce now. These two small devices not only reduce the drag, but also eradicate the lift and produce good downforce too. And that's largely because of the positive effects on the diffuser. So that is how you can easily improve the aerodynamics of the E92 BMW with just two little devices. If you're staying on YouTube, YouTube thinks you like this video, so check it out. Peace out, amigos.